This resource is the fifth in a 6-part series on exponents and logarithms. Part 1 defines exponents and logarithms. The exponent laws are defined, and justification for the exponent law of multiplication is provided. We consider how to transform between exponent notation and logarithmic notation, and define two special bases for logarithms. Part 2 explores expanding and contracting logarithms. Multiple examples of each are provided. Part 3 demonstrates solving logarithmic equations, with examples provided. Part 4 considers exponential equations. A general solution method is provided, and examples are given. Part 5 delves into solving exponential growth equations, with examples. Part 6 looks at solving exponential decay equations, with special emphasis on half-life problems. Many natural phenomena increase in size nearly without bound. One such example would be the amount of bacteria in a population. So long as the bacteria have a reliable food source, they will reproduce continuously. These types of phenomena can be modeled using exponential growth functions. Exponential growth functions have a form that look like a equals a sub 0 multiplied by e raised to the k times t power. The a represents the population size after a given amount of time. A sub 0 is the initial amount, or the amount at time 0. The k is a constant that determines the behavior of the equation. The t is the time that has elapsed. Exponential growth problems tend to take one of two formats. In the more simple type of equation, we need to find the population size after some given amount of time. The more involved problems require our finding the amount of time that needs to elapse to reach some population level. Let's look at the simpler case first. Unless we are incredibly lucky, we will be given just barely enough information to develop our formula. We are usually given the starting population size and the population size after some amount of time. We need to find the constant k. To do so, first we plug in what information we are given. Then we will divide the ending amount by the starting amount. Next, we take the natural logarithm of each side of the equation. This cancels out the e, and we are left with a constant times the amount of time equal to a natural logarithm. To find the constant, we divide both sides of the equation by the elapsed time. Now that we have solved for the constant k, we can set up our actual problem. Plugging in the required time, we are left with a problem best solved by a scientific or graphing calculator. Let's look at an example. Suppose we know that the population of a small European nation has been growing exponentially since the year 2000. The population in 2000 was 25 million, and after 3 years, the population was 30 million in 2003. We want to find out what the population will be in 2015. We know that the population level follows the generic exponential growth equation. We enter our given information. We know that the final population was 30 million, and the initial population was 25 million. We also know that the elapsed time was 3 years. We have sufficient information to solve for the constant, so let's go through the process. We divide both sides of the equation by 25. Sometimes we leave this division step as a fraction, but the result of dividing 30 by 25 is a nice decimal, so we can write it as 1.2. On the right side of the equal sign, the 25 cancels out, and we are left with e raised to the 3k power. Take the natural logarithm of both sides of the equation. We leave the natural logarithm of 1.2 as is, because we want to maintain precision as long as possible. On the right side, the natural log and the e cancel each other out, and we are left with 3x. Divide both sides by the 3. Using a scientific calculator, we find that the natural logarithm of 1.2 divided by 3 equals 0.0608 when rounded to 3 significant digits. We have our official model. The ending amount equals 25 times e raised to the 0.0608 times t. Because we want the population in 2015, we know that 15 years have elapsed since the growth began. We plug in 15 for t. Again, using a scientific calculator, we find that the model predicts that the population of the small European nation will reach 62.23 million in the year 2015. But what happens if you want to find the amount of time that has to pass until some target population is reached? Solving for time usually requires 2 passes through the basic steps of divide, take the natural log, and divide. We begin the process as before, by finding the constant of variation k. Then plug in the information we know. Divide the target amount by the initial amount. Take the natural logarithm of both sides of the equation. As before, the natural log and the e will cancel each other. Finish by dividing both sides by the constant k. Let's go through an example. Suppose we consider the population of Africa. In the year 1990, the population of Africa was 643 million. By the year 2006, the population had grown to 906 million. This begs the question, how long until the population of Africa reaches 2 billion people? Because our populations are given in millions of people, we can think of 2 billion as 2,000 millions. We know that the population growth is exponential, so we use the exponential growth equation. We insert the information that we know. The ending population of 906, the initial population of 643, and the time elapsed of 16 years. Divide both sides by the initial population. We opt to leave the division as a fraction, rather than being forced to round this early in the solution process. Take the natural logarithm of both sides of the equation. Again, we leave the result as the exact amount. We have the natural log of 906 divided by 643 equal to 16k. Divide both sides by 16. Using available technology, we find that the constant k equals 0.0214 when rounded to 3 significant digits. We have our full model. The ending population equals 643e raised to the 0.0214 times t power. We want to find how long it takes to reach a population of 2 billion. Since our populations are given in millions of people, we enter 2,000 for the ending population. Divide. Leave the result as a fraction rather than lose precision. Take the natural logarithm of both sides. The natural log and e cancel each other out. We are left with the natural logarithm of 2,000 divided by 643 equal to 0.0214 t. Divide both sides by the decimal amount. Using a calculator, we find that the elapsed time for the population of Africa to reach 2 billion will be 53 years. So according to this model, the population of Africa should reach 2 billion sometime in the year 2043. A general exponential growth has an equation that takes the form of the ending amount equals the initial amount times e raised to the product of some constant k and the amount of elapsed time t. While these equations look frightening, the solution method is straightforward. Divide, take the natural logarithm, and divide. We'd likely have to go through this process to even set up our equation by finding the constant k. If we merely want to find the amount after time, we can then plug in. Use a calculator to find the final amount. If we need to find the amount of time to reach a target amount, we need to go through another round of divide, take the natural logarithm, and divide. But what happens if the population is decreasing instead of growing? Stay tuned for the final chapter in the Exponents and Logarithms series.